in this video, I wanted to discuss what we refer to as arc length and sector area formulas, which actually has nothing to do with SOHCAHTOA at all, but just something I wanted to talk about and haven't really been able to fit it in anywhere else. Um, so basically, these formulas have to do not with triangles, but with what we refer to as circular sectors. So, like, imagine a piece of pizza cut out. A lot of people refer to pieces of pizza as triangles, but actually the true shape of a piece of pizza is not really a triangle, right? Because a triangle has three straight lines connecting its points, whereas like a piece of pizza, it's a slice of a circle, so it's really not a triangle, right? Because one of the edges is actually circular. And the proper name for such a shape is actually what's referred to as a circular sector, because it's like part of a circle, and it's not really a triangle. So if we're trying to solve properties of a circular sector, it's not actually going to be, we're not going to use any formulas for triangles, or they're going to have their own formulas. And those are the formulas I wanted to get into. So the first is what we refer to as the arc length formula, which is the way of figuring out how long is the arc on a circular sector. AKA, like, say we wanted to know what's the length of segment PQ, which is, going along the circle in this particular portion of this diagram. We want to, that's often what we refer to as the arc length, or, the length of the arc of that circle. So we refer to that as an arc, etc. But one thing is, if we want to, there's a formula which I wanted to talk just about for a second. It says that the arc length S, which is a common variable that we use for arc lengths in math, for reasons I don't want to get into, is equal to r times theta, which basically the radius of the circle times the interior angle. But something that's very important about this, or it's often also called the central angle of the circle, is the angle that you're using this formula must be in radians. If you plug in 60 degrees, the formula doesn't make sense. So let's just go ahead and say we didn't know that, and we said, okay, the arc length S is equal to r times theta. And if we were to just plug in theta in degrees, this is going to give us an answer, what, 9 times 60, which is 540 degrees. And it's like, well, like, what we're really trying to figure out is how long this line segment is. How does that answer make any sort of sense? So, because if this is 9, say, feet or inches or whatever, that's not going to be 540. It's quite clear that this formula makes no sense. But if I convert my angle to radians, then it will make perfect sense. Or really just need to convert this answer, because technically I'm answering it in degrees. But what is 540 degrees? How does that make any sense in the context of a circle? But basically, I could convert that angle from degrees to radians by multiplying by pi over 180, right? And that would then give me the angle in radian mode. And 60 over 180 is 1/3. Or as we know, that angle 60 degrees is equal to pi over 3. So notice if I just convert that angle from degrees to radians, now that answer is unitless and it will work in a formula. So it's just sort of something about certain mathematical formulas. Plugging in degrees is not necessarily going to make sense. And just why I wanted to bring this up is because in prior formulas, when we were talking all about SOHCAHTOA and whatnot, we were explicitly using degree mode as we were solving these, because those trigonometric functions, our calculator is capable of using degrees to work with the trigonometric functions. But if we're using formulas like this, which are not trigonometric, right? It's just a simple linear equation, something times something. It's not going to necessarily work in a degree mode setting, because the calculator won't really know to distinguish this multiplier. If you sort of see what I'm saying. But anyways, go ahead and finish into this math. Well, obviously 9 divided by 3 is 3, so this would give me 3 pi, which would be the length of the circular sector that I was looking for originally in this case. And anyways, that's what we refer to the arc length formula, and we could use that to find the length of the arc in a particular circular segment. And basically, you must convert your interior angle or your central angle to radians in order to use the formula properly. And the last thing I wanted to get into is, well, why? Why does this formula make sense? But if we think about the original definition of radian measurement, the radian measurement had to do with the unit circle specifically itself, where the corresponding angle would be referred to as in radians if it was the length of a circle, the length of the arc of a circle of radius 1. So say, for example, we're talking about pi over 3, aka 60 degrees, that particular location. We knew that had to be pi over 3 because we knew the circumference of the entire unit circle was 2 pi. And basically, if we're converting a degree measurement, we know a degree measurement, say, for example, 60 degrees, is a particular fraction of the entire circle. And if we multiply that fraction into 2 pi, that's essentially what converting from degrees to radians means. And we will get, well, 1/6 of 2 pi is pi over 3, and we can convert from degrees to radians, but it was based on the unit circle specifically. Now, say I was dealing with a larger circle, like in this case, we're talking about a circle of radius 9 instead of radius 1. Well, what's actually pretty simple about how the arc will behave is it obviously is going to be magnified, and just like how like triangles with same angles are similar, so are circular sectors as another basic property of geometry. Meaning that if I expand the radius by a factor of 9, the angle will also be magnified by 9, and if I just multiply that angle by 9, I will get the length of that arc. Basically, here I knew the angle and I knew the arc. If I just multiply them together, it will give me the arc length. It's remarkably simple actually at the end of the day, assuming I know what the angle is in radians. So anyways, radians times radius gives you arc length. And I'll leave you an example to try for yourself. And in the same way, say for example, you knew the ratio of the arc length to the radius, you could always reverse this and find the angle by the same formula. Because theta, if S is equal to r theta, well, I could also divide both sides by r to find theta. Theta would be equal to S over r. So, say I wanted to know, well, what is this angle? It would just be the arc length 100 divided by the radius 42, and that angle would be that exact value, 100 divided by 42, which is approximately 2.38. But what's important to know about that number is that just like before must be in radians, so this calculation is a radian measurement. And if I want to convert that to degrees, I could multiply by 180 and divide it by pi, as we know to do to convert from one to the other, and that would give me approximately 136.4 degrees. And again, like with triangles, these sort of calculations should pass the smell test, and those answers should seem about should make sense and seem about right based on the given figures. But anyways, it's a way of dealing with circular sectors, and if you want to solve angles or solve arc lengths, very simple. And the last little component of this is, what about area? Let's say, for example, in the same case, we wanted to figure out the area of a circular sector as opposed to the arc length. So like basically how much, let's say I was talking about my piece of pizza, and instead of knowing the arc length, and the arc length would be like, well, how long is the crust, which we figured out to be 3 pi. But instead I wanted to know how much, pizza is on there. What's the surface area of this particular segment, which we often refer to as sector area. There's another very similar formula for figuring out the sector area of a circular sector, which is going to be given by the formula 1/2 r squared theta, where again, theta must be in radians. So if I wanted to find the area of that, it's going to be 1/2 r squared times theta. Again, I need to make sure to convert 60 degrees to radians, which we've already done. So that would give me 1/2 of 81 times pi over 3. And 81 divided by 3 is 27. So this would be 27 pi over 2. And that would be the exact area, which would be in units squared, because it's going to change it from a linear unit to two-dimensional version of area. Say, for example, this was in inches. This would be in square inches. Excuse me. Or, of course, I could get a decimal approximation of that value, which is approximately 42.4 for the area. And also, well, why does this formula make sense as the last little component to this video? Is because it's kind of similar, where we could think of the circumference, this is a particular fraction of the circumference, but we could also do the same thing with area. So say we're going back to the unit circle. the to which we already know all the components of. The unit circle had a circumference of 2 pi, but if we're thinking about the area is equal to pi r squared, which is a formula that we haven't proven in this class, but is easy to prove in a lot of different ways. But the unit circle has a radius of 1, so basically the area of the entire circle is pi. And say, for example, I was looking at a particular segment, say, for example, with an angle of pi over 3. And say I was dealing with a larger segment, well, the area of that particular segment would not, if the area of the whole thing is pi, it would have to do with the particular fraction of the whole circle. So say, for example, like in the same way, it was 360, dealing with 60 degrees out of 360, that would be 1/6 of the entire circle. So basically, I'd be dealing with 1/6 pi for the area of this particular segment. And then again, if I have a larger radius, it would just magnify that area by a factor of that multiplier. But basically, if I take if I were to imagine an entire circle, the entire circle would have a radian value of 2 pi. And if I was to plug that in, notice that this makes sense. What I would get is the area is equal to 1/2 r squared. Let's just say with the unit circle we're dealing with 1 times 2 pi. Notice what I'd wind up with is exactly pi, the area of the unit circle. But essentially, normally the formula for area is pi r squared. But like basically for a sector, I'm normalizing this. Instead of using the full circle, which would be 1/2 of 2 pi, I'm taking 1/2 of the smaller angle, and I'm changing the value of that angle in dealing with this formula. And I know I'm not doing an incredibly great job of explaining this. There's another diagram in the slides which is a little bit easier of a way of kind of visualizing this. But normally I'll go ahead and bring this up just in case this makes more sense than what I've been trying to explain. But normally area is equal to pi r squared, and if I'm thinking about a particular sector, I'm dealing with some component of that. Basically, this angle is a fraction of the full circle. Theta over 2 pi would give me the ratio to the area part to whole. And if I multiply theta divided by 2 pi into the full area, basically 2 pi and the pi would cancel, and that would leave me with 1/2 theta r squared for the partial area of that particular segment. Anyways, that will wrap up this video on circular sectors. What I would recommend remembering is the formulas for these, and just make sure to use radian mode when you are plugging in.